होगी ये? औज़ु बिल्लाहि मिनश शैतानिर रजीम, बिस्मिल्लाहिर रहमानिर रहीम। डियर स्टूडेंट, अस्सलाम वालेकुम। Class 9 subject physics, chapter number 7, properties of matter, and the last topic of today's chapter is 7.9. Since we have already studied 7.7 and 7.8 topics, so our last topic is 7.9. Today we will discuss 7.9 topic, which is Hooke's law. Pages covered today 161, 162, and 163. Forget about 7.7 and 7.8 because we have already done this 7.7 and 7.8 in our last lecture. Today's lecture we will discuss 7.9, which is on page number 161. Okay, please open page number 161 of your 9th class textbook. I repeat, class 9 subject physics, chapter which we are doing 7 properties of matter, and topic of today's lecture is only 7.9, which is the last topic of this chapter. So pages covered so far will today 161, 162, and 163. Please open page number 161. This is the chapter we are doing, unit number 7, properties of matter, and we have discussed this one, ship and submarines, in our last lecture, and we discussed about elasticity, stress, and strain in our last lecture. What is elasticity? And this is the definition of elasticity. Stress we discussed force per unit area, and strain is change in length divided by original length. We discussed all this in last lecture. But in today's lecture, we will discuss about 7.9, which is Hooke's law, which is on page number 161. Please open page number 161 of your 9th class textbook. Okay. Hooke's law. Hooke's law, it has been the strain produced in a body by a stress applied to its directly proportional to the stress within the elastic limit of the body. So when we apply the force on the body, for example, we apply the force on the spring, you might have seen after the application of the force, the spring will stretch or compress or stretch under the action of the force. What will happen? So here is a spring attached to the strand. So its one end we applying the weight on its one end, and one end is fixed over here. So if we keep on applying the load, the spring will be stretched and it will be stretched, keep on stretching within the elastic limit. So as much as we apply the force, the strain will be produced as well within the elastic limit. What does this mean? Within the elastic limit. So if you have a comb in your hand, what will you do if you apply the force over here, but if you release it, it will come back to its original position. But if you apply more force, it will be and you release it, it will come to its original position. But there is a limit. If we applied more force, and what will happen, it will break and it will never come back to its original position. So this is called elastic limit, where after the application of the force, the body will destroy, the thing will destroy, the comb will destroy. That is called that is not the elastic limit, that is out of elastic limit. But Hooke's law is applied within the elastic limit, where suppose you have a spring here, its one end is attached and the other end is fixed. The other end we have keep keep putting the loads in here, weights in it, in one pan. We are keep putting the weights. What happens if we apply the weight over here? It will keep on stretching. But there is a point will come when if we applied more weight, if we put more weight in it, the body will become damaged, or the body will not come to its original position. That is called out of elastic limit. But Hooke's law is only applicable within the elastic limit. The strain produced in a body by the stress applied to it is directly proportional to the stress within the elastic limit of the body. So stress is directly proportional to strain. What will happen if you divide this? Whenever you solve directly proportional sign, I have told you so many times, when the directly proportional sign is replaced with equals to and some constant of proportionality. So stress is directly proportional to strain within the elastic limit. Within the elastic limit, stress is directly proportional to strain within the elastic limit. If we stress is if we are putting the weight in the in the spring, the extension will occur. The body will extend. The spring will be stretched. This is called strain. So if we keep on putting if we remove this weight, where the body will come to its original position. So stress is directly proportional to strain. So within the elastic limit. So if you remove the directly proportional sign, it will come with equal sign and some constant of proportionality. So if you want to find out the constant, so stress strain is multiply here. If it is go on the other side, it will be divided. So stress divided by strain equals to some constant. Hooke's law, the name of the scientist is Hooke. Hooke's law is applicable to all kinds of deformation and all types of matter. Where Hooke's law is only applicable within the elastic limit, where the body will not change its position. It will come back to its original position, that is called the elastic limit. So Hooke's law is valid or applicable for all types of matter, whether it is solid like pen, so it is liquid or gases within the certain limit. This limit tells us the maximum stress that can be safely applied on the body without causing permanent deformation in its length, volume, or shape. In other words, it is the limit within which a body recovers its original length, volume, or shape after the deforming force is removed. Suppose this is the force, we applied the force over here. What will happen if the body will stretch under the application of the force? If we keep on extending the force, adding the weight in the pen, what will happen? There is a time will come where the body will break. Look, there is a they have plotted the graph between force and the extension. Extension is taking on x-axis and the force is taken on y-axis. If we keep on extending the force, the spring will be stretched. Okay, keep on stretching. But it will if we remove the force, what will happen? The body will come back to its original position. This is the point where the body will come to its original position. But this is the point. This is the elastic limit. The After this, the body will be either destroyed or will not come to its position after this blue point. After this blue force, if we apply more force on the body will not come to its original position, but either it will be destroyed or the permanent deformation will be in the body. The body will change its shape and will not come back to its original position. For example, if I have a spring in my hand, what we have, if I stretch it, if I apply the force on one end and remove the applied force, what will happen? The body will come to its original position where it is starting. If I apply force here, so if I release the force, the body will come to its original position. There, here, if I apply the force, if I remove the force, the body will come to its original position. But if we apply the force over here, this is the last point where if I apply the force, the body will come to its original position. But after this point, if I apply more force, what will happen? Either the shape of the body or the volume of the body will change and the body will not come to its original position. And this is the point, if I apply the more and more, keep on more apply the force, you might have seen the body will break and will never come back to its original position. So within the elastic limit, this is the elastic limit. After this, Hooke's law is not applicable. Hooke's law is applicable from this point to this point. This point, only elastic limit. So if we keep on applying the force and release the force, the body will come to its original position. If we applying the force over here, the body will come to its original position. But after if we apply the force, and if we release it, there will be the change in the shape and the body will not come back to its original position. and there will be the deformation caused in the spring, and the body spring will not come to back to its original position. So what will happen if I apply more force over here? So the body will break, the spring will be break, and it will not come to back to its original position. The Hooke's law is only applied within the elastic limit. So here, stress is directly proportional to strain in this limit. From here to here, stress is directly proportional to strain. And when we remove the directly proportional sign, we get equal and some constant of proportionality. If we want to find out the constant, here strain is multiplied. Then if we come on the other side of the equation, it will be divided. So stress over strain equals to some constant. So Hooke's law is only applied within the elastic limit. Now I move towards Young's modulus. And Young's modulus is on page number 162. You please open page number 162 of your 9th class textbook, because we are going to start Young's modulus. Young's is the name of the scientist, physicist. Consider a long bar of length L0 and the cross-sectional area A. Let an external force F equal to the weight W such that the stretched length becomes L. According to the Hooke's law, the ratio of the stress to the tensile strain is constant within the elastic limit of the body. You know this. we are considering a long bar of length. There is a there is a there is a length of like a ruler. It's suppose it has a long bar of length. Its length is original length is L naught. L naught means the its original length, and cross sectional it might have it has some cross sectional area, and I suppose I denote this cross sectional area with capital A. What happen? Let an extension force F equal to the weight W stretched to such that the stretched length becomes L naught. If we apply some force on it, and it will change its length from L naught to L. So according to Hooke's law, the ratio of the stress to the tensile strain is constant, as I have already discussed. Here, stress is direct. The ratio of stress to the strain equals to some constant. So Young's modulus, the ratio of stress to the tensile strain is called Young's modulus. The ratio of stress to the tensile strain is called Young's modulus. Suppose stress is change in length of the rod is delta L. So what was the original length? L naught, and the change in length is capital L. So what will be the change in length? The minus bigger value minus the lower value. So L minus L naught will be the change in length. So you know the formula for the stress is force per unit area. As we have already discussed in my previous lecture, stress is defined as force per unit area. So what will be the force? F divided by A. This is the formula for stress. Stress is force per unit area, F over A. What is the tensile strain? And you have already studied the tensile strain, the change in length divided by the original length. So what is the change in length? L minus L naught, and the original length is L naught. So change in length is denoted with delta L. So L minus L naught is denoted with delta L divided by L naught. So Young's modulus formula is stress divided by strain. So what is stress? Force per unit area. So putting the values, stress is F over A, and tensile strain is delta L over L naught. If you solve this, this L naught will be on the top and delta L will be at the bottom. So F over F L naught A delta L. So this is my Young's modulus, and Young's modulus is denoted with capital Y. Young's modulus is a letter. We denote Young's modulus with capital Y. SI unit of the Young modulus is Newton per square meter, because L unit of length is meter, and this unit of length is meter. So this meter will be cancelled with this meter. And what is the unit of force? Force unit is Newton, and area unit is meter square. So its Young's modulus units will be Newton per meter square. Young's modulus of some common materials are given in tables. So you can see Young's modulus of aluminium is 70 into 10 to the power 70 into 10 to the power 9 Newton per meter square. Similarly, bond has a Young's modulus value is 0.02 Newton per into 10 to the power 9 Newton per meter square. Copper is 110. So different values are given for Young's modulus for different material. So I told you the ratio of the stress to the tensile strain is called Young's modulus. So Young's modulus formula is stress divided by strain. First of all, we use the formula of stress. The stress we have discussed in our last lecture. So this is the stress formula. Stress is force per unit area. I'm just putting this value. And the tensile strain is change in length divided by original length. So uh, stress is force per unit area and tensile strain is L minus L naught divided by L naught. Change in length divided by the original length. What is our change in length? Change in length is denoted with delta L. Delta L is equal to L minus L naught. Just put these values. Just use this formula L minus L naught divided by L naught original length. L minus L naught is the delta L. Delta L divided by L naught. You know the formula for Young's modulus is stress divided by strain. Just putting the values of stress. Stress is F over A and tensile strain is delta L over L naught. Just plug in the values in this formula of Young's modulus. So our Young's modulus will be F L naught A delta L. So since we want to find out the unit of SI unit of Young's modulus, you know the unit of length is meter and unit of this length is meter. This meter will be cancelled with this meter. So unit of force is Newton and unit of area is meter square. So if you take meter square on the top, it will be m minus 2. So SI unit of Young modulus is Newton per square meter, which is denoted with nm minus 2. So these are the different values of Young's modulus of for different material. If you have aluminium, its Young's modulus value will be 70 multiplied by 10 to the power 9 Newton per meter square. And it is bond, Young's modulus value is 0.02. And similarly, if you have steel, its Young's modulus value is 200 multiplied by 10 to the power Newton per meter square. Now we solve the example 7.7 by using the Young's modulus formula. This formula we will use to calculate the Young modulus for steel. And this is my answer over here. Okay, we solve this now. A steel wire is 1 meter long and cross-sectional area A 5 into 10 to the power minus 5 meter square is stretched to 1 millimeter by a force of 10,000 Newton. Find the Young modulus of the wire. First, example 7.7. A steel wire 1 meter long and cross-sectional area A is 5 into 10 to the power minus 5 meter square is stretched through 1 millimeter by a force of 10,000 Newton. Find the Young's modulus of the wire. So I'm going to write the given data. Force is given to me. This is the force is given to me, which is 10,000 Newton. So my capital F will be 10,000 Newton, which is the force. And length is, original length is given to me 1 meter. This is the steel wire 1 meter long. It means L naught is 1 meter. Excuse me. Is stretched through 1 millimeter by a force. Extension is 1 millimeter. So you need to convert this into meter. You know milli is 10 to the power minus 3. So if you divide this 10 to the power minus 3, you will get 0.001 meter. Because the SI unit of length is meter, that's why I have converted this millimeter into meter. The extension or change in length is 0.001. And area, cross-sectional area is also given to me, and cross-sectional area is given to me 5 into 10 to the power minus 5 meter square. So cross-sectional area A is equal to 5 into 10 to the power minus 5 meter square. These are all things we will use in this formula to calculate the Young's modulus of wire, Young modulus of the steel wire. So we will calculate this now because you know the Young modulus of steel wire is 200. So we will calculate this one. This is 10 to the power 9. Okay, 200 into 10 to the power 9 Newton per meter square. We have seen in the table. Now we are calculating with the help of this formula. Young's modulus formula is capital Y is equal to F L naught A divided by delta L. So you have seen this, a steel given data, length L node is 1 meter and force area is 5 into 10 power minus 5. This is the area given to me, and force is 10,000 Newton. This is the force Newton is given to me, 10,000 Newton. And change in length or extension delta L is 1 millimeter. I converted this into SI by dividing in 10 power minus 3. So 0.001 meter is my four things I have calculated in given data. It's given. Now I'm going to find out the Young's modulus, which is capital Y is equal to F L naught A delta. I will use this formula 7.12 in my example 7.7. So I use the formula capital Y is equal to F L naught divided by A delta L. So value of F is 10,000. I have already told you. I show you now. Capital F value is 10,000. L naught is 1 meter. Delta is 0.001 meter. And area is 5 into 10 power minus 5. So capital Y is equal to F L naught A divided by A delta L. So F is 10,000. L naught is 1 meter. A is 5 into 10 power minus 5. And delta L is 0.001. So if you calculate this, if with the help of the calculator, you will find 2 into 10 power 11 Newton per meter square. This is because the unit of Young's modulus is Newton per meter square. As I have already told you, the unit of Young's modulus is Newton per meter square. So this is I have calculated Young's modulus, which is 2 into 10 power 11 Newton per meter square. So in the table, we discuss the table. So its value of steel is 200 into 10 power 9. If you calculate 2 into 10 power 11 into this equation, 200 into 10 power 9, you will have uh, the same value of steel. Capital Y is equal to 2 into 10 power 11 Newton per meter square. I repeat, a steel wire, or first of all, we calculate the Young's modulus. Young's modulus, formula of Young's modulus is capital Y, stress divided by tensile strain. Uh, uh, okay, Young's modulus capital Y is stress divided by strain, tensile strain. So we calculate the stress. In my last lecture, we discussed about stress, and stress is force per unit area, that is F over A. And tensile strain, I show you, tensile strain is change in length divided by original length, and change in length is denoted by L minus L naught divided by original length, L naught. So change in length will be L minus L naught divided by L naught. I show you stress is force per unit area. This is the stress. Stress is force per unit area. I use this formula for stress, and I use this formula for tensile strain. And tensile strain is change in length divided by original length. So Young's modulus capital Y is equal to stress divided by strain. Stress divided by strain. So stress is force per unit area, and tensile strain is L minus L naught divided by L naught, which is L minus L naught is equal to delta L, delta L divided by L naught. So I put this value, stress value and strain value, in this formula. Young's modulus is equal to stress over strain. Stress is F over A, and tensile strain is L naught, because because it will come under tensile strain. But if you reverse this, it will be L naught divided by delta L. So Young's modulus formula will be capital Y is equal to F L naught A delta L. Now we find the SI unit of the system international. The unit of Young's modulus is the Newton per meter square, because this is the length unit is meter, this length is unit is meter, this meter will be cancelled with this meter. So the force unit is Newton and the area unit is meter square. So our Young's modulus unit will be Newton per meter square. By using this formula, capital Y is equal to F L naught A over delta L, I solved the example 7.7. So this example is a steel wire is 1 meter long and cross-sectional area A is 5 plus or minus 9. Now I'm going to write the given data. Force is given to me 10,000 Newton. You can see this is the unit of force. Newton is the unit of force. The force is 10,000 Newton. Okay. L naught is the original length. This is the steel wire is 1 meter long. It means length of steel wire is L naught, which is original length 1 meter, and area is 5 into 10 to the power minus 5 meter square. This is the area unit. And extension is also given to me and is stretched to 1 millimeter. It means extension is delta L. Delta L is equal to 1 millimeter. So milli, you need to convert this into meter because the SI unit of length is meter. So you divide this into 10 to the minus 3. So you will get 0.001 meter. So using all these values in this formula, capital Y is equal to F L naught A delta L. Use this formula to calculate the Young's modulus, and the Young modulus of steel will be 200. You can see in the formula in the table 200 into 10 power 9 Newton per meter square. So I use this formula, capital Y is equal to F L naught A delta L. F is 10,000. L naught, I show you, L naught is 1 meter, and delta L is 1 millimeter, and area is this 5 into 10 power minus 5. I use this in this formula. F is 10,000. L naught is 1 meter, and area is 5 into 10 power minus 5, and delta L is 0.001. I show you we have converted this 0.001 meter. So I substitute all these values in this formula, Young's modulus formula, and Young's modulus is capital Y is equal to F L naught A delta L. I just substitute all these values, force, original length, area, and extension in this formula. And when I solve this with the help of the calculator, I will find the value of steel wire will be Y, capital Y, Young's modulus of steel wire is 2 into 10 power 11 Newton per meter, because you might have seen the Young modulus value in the table is 200 into 10 power 9, but here it is 9. But if you convert this into 11 to 200, so you will get the same value as in the table. Capital Y Young's modulus value is 200 into 10 power 9 Newton per meter square. So our Young's modulus value of steel is 2 into 10 power 11 Newton per meter square. So student, this is the end of the chapter. Today we have ended the chapter. So in our next lecture, we will discuss the MCQs of this chapter and the and the numericals. We will try to solve the numericals. So this is the end of the chapter today. If you have any questions regarding today's topic, please let me know. Memorize the topic covered in the homework is memorize the topic covered in today's lecture by heart and write them once on rough register and solve examples on rough register. I will not check the rough register. I will check only the neat registers of problems we will discuss of this chapter. Problem number 7.1 to 7.12. I will check only for these numericals. I will not check the rough work. This is for your practice. For homework, this is for your practice. Okay. Memorize the topic covered in today's lecture. The topic which we covered, Young's modulus, and the topic which we discussed today is Hooke's law. Try to memorize this by heart. Hooke's law. Try to memorize this by heart. These are the figures which are very important according to the Hooke's law. So Young's modulus we discussed today. Please try to memorize this and also solve the example 7.7 which we discussed today. Please keep on going, keep on memorizing your topic side by side because it is very important. Don't make your work pile up. So in order to make clear understanding, you should work side by side, or you should memorize the things, or you should learn the things side by side, because it will help to digest you. It will help you to understand the topic very clearly. Please try to understand. Uh, uh, try to memorize your topic as early as possible. Okay. So memorize the topic covered in today's lecture by heart and write them once on a rough register and solve example which we discussed today, example 7.7 on your rough register. The students, if you still have any questions regarding today's topic, please feel free to ask questions. Don't feel shy. Don't feel embarrassed. Make courage and ask questions regarding today's topic. Thank you. Please, Aline, Marinisa, Usman, Mubna, unmute your mic and ask questions. If you have any questions of today's lecture, please feel free. Yes, Mubna. Mubna, please unmute your mic and ask questions if you have any questions in today's lecture.